The next kind of transformation that we'll be looking at is the rotation. Here I've got an image of a time-lapse photography image of the sky at night, focused at Polaris. Polaris is the this one here that it didn't get like a full night's revolution of the rotation of the Earth. But due to the rotation of the Earth, we see, if we expose our camera correctly, we see these streaks across, these elliptical streaks across the film that make it look like there's these little circles or whatever. And if you'll notice, most of them are making like quite large ellipses, versus Polaris, which makes a rather small little oval there. And what this is showing us is that there is a center somewhere that, if it was a star, it would just be a dot. And that is the center of rotation. We'll be talking more about that later. These other straight streaks are probably just airplanes flying across, or possibly meteorites or satellites or something. But the rest of these elliptical streaks are from stars due to the rotation of the Earth. And that rotation is based upon a fixed point called the center of rotation, which is what the axis of the Earth points at, some imaginary spot in the sky. Let's review some things that we've talked about before. So rotation is when you turn or spin a figure around a point, and it's got to be a fixed point like that one that all the stars were spinning around, called the center of rotation. I should get this down here. Okay, what we need to know in order to do a rotation is, where is the center of rotation? So we need to know the center of rotation, and I'm just going to say center of R here. We also need to know what the angle of rotation is. And we need to know if we're spinning or rotating the thing clockwise or counterclockwise. For the convenience of this class, we're always going to be sticking with clockwise rotations. Later on in physics classes and other more advanced math classes, you'll be using counterclockwise just by convention anyways. So we're just going to get in the habit of doing that now. Clockwise rotations, if we ever were going to do those, they would need to specify and tell us, hey, this is a clockwise rotation, not a counterclockwise rotation. This other image that I've got here shows a geometry book being rotated 90 degrees counterclockwise about this fixed point here. The whole reason that I've shown you this image, and I've got this on this page, is that I want you to see that the orientation gets changed, but the image itself is congruent to the pre-image. All of the lettering and everything is all the same, size and shape. The only thing that is different here is where the position of the image is and its orientation got turned. If you had a protractor and saw image and pre-image and saw, the direction of rotation and everything, then you could actually overlay your protractor. Overlay your protractor on top. Well, this isn't exactly going to work, is it? Well, let's go to the next screen. And with it overlaid on top of the center of rotation, so you've got this little part here, the big dot, or where the protractor rays all meet here, okay, at that dot. I've overlaid that on top of the center of rotation. And then you can use your protractor to actually measure the rays that go out along the different points, to the image and pre-image points. You can then measure that with a protractor to say what the angle of rotation is. But to make it simple this year, again, we're just only going to be doing 90 degree, 180 degree, and 270 degree rotations. If we did a 360 degree rotation, that's just going to put the image right back on top of where the pre-image was. And those aren't interesting, so we won't really be looking at those. Here are some coordinate rules for rotations about the origin. If your pre-image is located at A, B, that would just be the x and y coordinates of the pre-image point. Then after a 90 degree rotation, the image is going to be located at -B, A. What that means is, whatever the y coordinate was for the pre-image, change the sign of it. So if it was positive, make it negative. If it was negative, make it positive. And that becomes the x-coordinate of the image. And then use the x-coordinate of the pre-image as the y-coordinate of the image. I don't know if I said pre-image there. Use the x-coordinate of the pre-image as the y-coordinate of the image. That time I said it correctly. Okay. If you've got a 180-degree rotation, again starting with points A, B, then just change the sign of both the x and the y coordinates, and that tells you where to find the image, in this case the green one. It would be located just as far from the origin as AB was, just in the opposite direction, with a 180-degree rotation about the origin. The next one to look at is the 270-degree rotation, where your your x-coordinate becomes the opposite of the y-coordinate in the image, and the y-coordinate, which is B, becomes the x-coordinate of the image. Okay, let's this all might be confusing. You probably want to jot something like this down in your notes, and let's go ahead and use that in an example. So we've got quadrilateral RSTU, and they give us the coordinates up here at the top. They then say to rotate this with a 270-degree rotation about the origin. So here we've got our pre-image points all set up, kind of in a table like we've been doing. And the rules for this one I've written down, or have already been written down for me. We need to use B, negative A. So again, I'm going to be using as my x-coordinate the y-coordinate from the pre-image, and as my y-coordinate for the image, I'm going to be using the x-coordinate from the pre-image, or the opposite of the x-coordinate from the pre-image. So let's go ahead and apply that now. For r prime, I'm going to have the point 1, negative 3. Take a second to make sure that you understand why and how I came up with those numbers. Go back and look at the rule for this 270-degree rotation just to make sure that I've done this correctly. So for s prime, then I should be using 1, negative 5. For t prime, I should be using negative 3, negative 5. And for u, I should be using negative 1, negative 2. Again, take a moment just to verify and make sure that I have done all of these correctly and that you understand exactly how that works. Pause if you need to, look this over. You can notice that it is verified by the graph that the image, the red figure there, has the vertices all labeled and plotted exactly how I had just come up with them. So all of my image points have been plotted the same way that I have calculated them using the coordinate rules. Let's take a look at an example where we don't have a graph. Triangle JKL with vertices at 3, 0, 4, 3, and 6, 0. Rotate the triangle with a 90-degree rotation about the origin. Again, that's going to be counterclockwise. This time I had to set the little table up myself, but I've written down my rule in red there for the 90-degree rotation, that AB gets mapped to negative B, A. So let's go ahead and apply that for my problem here. J prime is going to be found at, well, negative 0 is still just 0. And then I'm just going to use A, which is 3, as the y-coordinate. K prime is going to be at negative 3, because I'm using the opposite of the y-coordinate there. And I'm going to use the x-coordinate as the y-coordinate for the image. So 4. L prime is going to be found at, again, the opposite of 0 is just going to be 0. 0 actually doesn't have an opposite. You can't change the sign of something that doesn't have a sign. But the A here is going to be 6, and so I'm just going to use 6 as the y-coordinate for the image. So here is where the image would be located at those 3 vertices. If I had a graph, I'd plot it, and then I would connect the dots and have my image. But since I don't, I'm done. Here are a couple of problems for you to do that we'll be using in the warm-up tomorrow. Please make sure that you remember these are counterclockwise rotations. So use the rules that we've come up with